So this is the idea. We're gonna draw some ellipses here, and the idea is if you take a string, gotta be a string, can't be like a rubber band. So the string, and you tie it into a loop. Okay, this kind of represents. Can you see it? This represents almost the idea of the gravitational pull, where the gravitational pull is always kind of the same. Okay, and when you have something that's an ellipse, it's that you're going to have, the shape's going to be built from this gravitational pull. So what Kepler said was that the paths of ellipses, or paths, I'm sorry, of planets travel in an ellipse where the sun is one of the foci. So right now, foci is just plural for focal point. So I have two push pins, and those two push pins are going to represent my foci. And those two push pins are pushed in, are going to stay there and aren't going to move. So let's say that the white one here is one of the focal points. That'll be the sun. So all I need to do now is trace with this string and see what I'm going to get from here. So I trace it along. All right, there. And I get some type of ellipse. Okay, so there's my ellipse. Now, to figure out what the eccentricity is of that ellipse, all we'd have to do from here is measure the distances between my two foci, okay, from here to here. All right, we use the letter C for distance between foci. All right, then we would measure the total distance along this line, which is the longest distance you could get. We call this the major axis in math. So this distance here, all the way across to there, is going to be the major axis, which we give the letter A. Okay, so that whole distance here is A. All right, and the eccentricity is just going to be, so E for eccentricity is just the distance, C, distance between the two foci, divided by A, the major axis, the longest point, the longest distance you can get in that ellipse. So let's try another ellipse. Let's see if we get it further apart. Okay, so now we go further apart with this. And I'm going to line up where my distance is here. Hopefully it's long enough for my string, but I'm going to go here, far apart. Make sure I don't go too far here, to there. So now I'm going to have a much longer ellipse, a much longer distance between foci. So now I do it again. Trace it now. What am I going to get? Well, extend it all out. Oops, my string got a little messed up there. That's okay. Okay, so now here's a much longer ellipse. Okay, so my distance between foci, now we measure it again. So here's my C, my distance between the two foci. And here's my distance, the major axis, okay, which A. And so now what we'd see is that the distance between foci is closer to the distance of the major axis, so you'd have a more eccentric ellipse. So you'd have a higher eccentricity, and compared to the old one, okay, this one looks more like a circle. This one you can see looks more like an ellipse. Okay, let's try one last thing. So what about if we have something that's going to be one focal point on top of the other, so two foci on top of each other? What's that going to look like? All right, so in this one here, basically you have just one focal point. What's the shape you get? Well, if you trace it along, I'm going to hold it down. I'll fall off the paper a bunch, but you'll get the idea. All right. The shape you end up getting is a circle. So an ellipse is somewhat is as similar as a circle. It's just that a circle is an ellipse with the focal points on top of each other, and that's what you end up drawing. Okay? So then thinking about it here, when you have other shapes, so this is a circle, that's a much higher or a much higher eccentricity because the focal points are much closer to the axis. All right? And this one, if you looked at that picture normally, you would say, oh, that's probably a circle, you know, if you just guessed by the shape. But then you realize, no, you got the focal points a little bit further away from each other. And the whole idea that was big for Kepler is that when you calculate this eccentricity, this is even more eccentric than the planets that Kepler was able to use the data from Brahe and figure out about eccentricity. So it's such a hard, precise thing that Kepler was really good, and he could have gone to some other planets that even had less eccentricity than the one he picked. Okay? But that's the whole idea with eccentricity.